Hello everyone and welcome back to the channel. In today's video we'll be looking at reading some inputs, and today's device that we're going to be reading is a button. So this is a very cheap 5x6mm button that you can get from anywhere really, and this is how it works. So you have two contacts. Okay, so this line over here is one contact, and this line over here is another contact. So this is internally, this is internally connected to this, and this is internally connected to this. So when you press on the button, this contact is connected to this contact, so this and this are connected. But you need to remember that when you wire the button, you do not connect this into this because these are connected to each other by default. So I'm going to just connect the button first and you will see what I mean. So over here we have one contact, and over here we have one contact. So if I put it like this, okay, let's make it a bit more clear. So I have the button in this position. I'm just going to rotate it like this. Okay, so stick it in. So this contact, this is one contact, and this is one contact. So it means that when I connect one pin to here and one pin to here, when I press the button, it connects. When I release the button, they do not connect. They are disconnected. So that's just a bit of the quick breadboard placement. And now let's discuss how that actually looks like. So firstly, I'm going to draw out how the button actually is. So this is the button. We have this pin, this pin, this pin, and this pin. So as I mentioned, at the bottom of the button you see that there's this column. So this is a column and this is a column. This represents the internal connection. So this means that internally this whole long piece is 1. So it means that this pin will always be connected to this pin. Likewise, this pin will always be connected to this pin. So when you make a connection, if let's say you were to draw this as a switch, then this whole thing would be one end of a terminal, which is like this, and then this whole thing would be another end of the terminal, which is this. So when you press the button, this internally connects to this, and that's how the switch closes. So that's how this thing is. So hopefully that clarifies how we should orient the button. Okay, now let's look at the ways we can connect the button or switches, because a button is basically just a switch, to the Arduino. So before we do anything, let's do a bit of planning. So the first thing we have to know is that pins, or input pins specifically, must not be floating. So what is floating? So floating means that your pin is in an undefined state. So imagine you have a pin which is, say, pin 10, and you do not connect anything to it. So it's just connected to the board. This is the Arduino Uno, and it's just left as it is, but you say pin mode is input and you start reading a value. So what happens if you do that? Well, since this is assuming that the pin 10 is really not connected to anything, the value of pin 10 can be anything between 0 to 5 volts, because there is no reference, there's no benchmark, or there's nothing to tie it down to any reference point. So it's just going to be able to float or bounce around, literally. So if you took a snapshot of the serial plotter, you would actually see the value just bounce around randomly. That's actually what happens, and that's not good. So what do we do if we don't have anything connected to the pin, or perhaps if we have something connected? Say we have this switch that actually connects the pin to 5 volts when it's closed, but when we open the switch, this is not connected to anything because this switch is open. We need to put a resistor and then bring it to ground. Why is this so? This is because when nothing is connected to it, at least there is a resistor, and because there is no current flowing through this, so therefore the voltage across this is 0. So this actually is also at ground potential. Of course, it's not connected to ground, it's just at ground potential, which is 0. So this pin is not floating, it has been pulled to ground. So we call this the pull-down resistor because it pulls the pin to ground when nothing is connected to it. So that's a pull-down resistor. As you can imagine, there's also what is called a pull-up resistor. So assuming that we have a pin and then we want to connect it to ground when we close the switch. So in this case, when the switch is open, we put a resistor, and as you can imagine, we connect the other end of the resistor to 5 volts. So what happens is when the switch is open and nothing is connected to the switch, this is not connected, the resistor, no current flows to the resistor because we assume that the pin has a very high resistance. Internally, the Arduino Uno has a very high resistance on the pin, so very negligible current flows through. So this over here is also at 5 volts, and this pin is not floating because it has been pulled up. It has been pulled to the 5 volts reference voltage, and we call this the pull-up resistor. Okay, so with that being said, we can actually draw out the two possible combinations of a button. So if let's say we have pin 10 over here, we can either have a pull-down resistor, let's say PD, pull down, and then we connect the button to 5 volts. So this is one combination. This is a pull down combination, or we can have a pull up combination where we put the switch to ground and then we pull the other end to 5 volts. So this is RPU, or pull up. Okay, so let's look at the cases. So in the case of the pull down resistor, what are the cases? So the first case is button is pressed. So on press, what happens is this closes. So the circuit is closed and 5 volts comes down. Oh, it sees the resistor. It's okay because it's a resistor. It's not short circuiting because there is resistance between this and ground. So it's not just going to rush the ground and cause a short circuit. It's actually going to, some current will flow through this resistor. The current, of course, will be related to the ratio of the voltage to resistance. But usually we set this at around 10k or so, so the current is really very small. But the important thing is now, since this resistance over here is negligible, this is going to be 5 volts because no voltage is dropped across this switch. That's assuming the switch is like an ideal switch. It has 0 resistance. So this pin will read 5 volts, and this 5 volts will drop across this remaining resistor and go to ground. So when we press, we will see high, which is 5 volts, because 5 volts goes down, 5 volts here. So that's on press. On release, okay, I'm running out of space, but I hope you can see what's going on. On release, this is the initial case when we open the switch like this. Okay, what happens is 5 volts cannot come to here, so 5 volts, so this is actually just going to be floating, so-called, but we have our resistor that is going to pull this to ground. So no current flows through this, therefore no voltage drops across this, so here is also 0 volts. So now we record low because this pin sees 0 volts or ground. Okay, so that's how it works. How about the case of the pull up? So as you might expect, this is literally an opposite. So you might be really, you might deduce that on press, this should be low, and on release, this should be high. And you are absolutely right, because let's just go through this once more. On press, this is connected. So, well, this pin is going to see 0 volts because there's 0 resistance to this switch, so this is essentially just going to be connected directly to ground. That is true. So it sees 0 volts here, and because 5 volts drops across this resistor, some current flows through. Current is going to be related to the ratio of voltages to resistance. It's a large resistor value, so it's not going to be a lot of current, and we will still see 0 volts. So this means it'll be low. And when we open the switch, well, what happens is current stops flowing. Okay, now this is infinite resistance, and 5 volts, no current flows through because here is high resistance as well. We assume that no current flows into the MCU, into the microcontroller. So this is also going to be 5 volts. So this will read high. So as we can tell, the pull-up configuration essentially inverts the logic, because when we press the button, this is low, and when we release the button, this is high. Whereas this is non-inverting, because when we press the button, this is high, and when we release the button, this is low. So this actually is the more so-called, I won't say it's the correct setup, but it's a more straightforward, and it really makes more intuitive sense, because when you press a button, you expect it to be high and not to be low, because, well, you're actively pressing the button, so you assume that the input goes high. But in the case of the pull-up resistor, that is not the case. So, okay, with that out of the way, we can actually start to do some breadboarding. So, okay, we've put our switch down. I have already configured the positive and negative rails. We are going to make some connections. So the first things first, we're going to get ourselves a resistor, because as I mentioned, we need a resistor to do the pull up, pull down. Okay, once again, as per standard practice, we're going to check the resistor value, make sure it's 10K. So I'm going to put mine at 20K, and then going to just test. So put it on these two. Oh, this is not 10K, this is 100 ohms. That must be from the previous project. How about this one? Also 100 ohms. Blimey. I did recall taking out a 10K resistor. Never mind. I can get one right now. Okay, I've just taken out one 10K resistor. Hopefully this is indeed 10K. And bingo, it is. Okay, so put this aside. Now we are going to use the pull down configuration first. So as mentioned, we connect one prong of the switch to this and one prong of the switch to this, never one to this and one to this, because these two are internally connected by default. So one end goes to the ground, so the resistor pulls the button down to ground, and the other prong of the switch goes from is connected to 5 volts, because this is the pull down configuration. Okay, so now that it's done, last thing we have to do is we have to connect the other end of the switch to the pin that we're going to use to measure. In this case, we use pin 10. So the other prong, or the prong that had the resistor, goes to pin 10. So 8, 9, 10. Okay, so over here we have a very simple pull down resistor combination with the button. And now let's go to the Arduino IDE and let's start writing some code. Alright, so we are back in the Arduino IDE, and let's write some code to read the state of our button. So the first thing we need to do is we need to configure our pin to be an input pin so that it can read the button. So we will use the pin mode function, and the first argument is the pin number, and the second argument will be our mode. So we have three options: input, output, and input pull up. For the purposes of this button, we will use input instead of input pull up, because we are using the resistor to pull down. In later on, we will talk about when to use input pull up, but for now, because our resistor is in a pull down configuration, we use input. Okay, so that's done. Next, we will set up the serial monitor. So serial.begin 115200, and then we will go into our main loop. So the first thing we'll do is that we will take a reading of our button. So we will create a Boolean variable called button reading, and we will let that equal to be the state of our button. So we use a digital read command, which will return, or it would give us the value of the pin that is being read. So you read the pin and give the value. So we assign that value to this Boolean, which is button reading. So a Boolean variable is like a digital variable. It only has two values, true or false, which is perfect for this digital read, because digital read can only be true or false. Okay, and then we will print a line which will say current button state, and then we will print this value out. So button reading. So that's that, and we will delay 1 second because we want to not spam the serial monitor with all these readings. We would just like to wait for 1 second and then repeat everything again. So we will upload this code. I have my board connected on COM10. Once again, we can check it is indeed on COM10. So I will select COM10 and Arduino Uno, and we will upload this code. So in the meantime, let's get back to our setup and let's see how this all runs. Okay, so we are in the serial monitor, and I've got the setup over here, And let's see what's going to happen when I press the button. So I'm going to press the button now, and we see that it goes from 0 to 1. I release the button, and it goes from 1 to 0. So that's all good, and everything's fine. So we might think that this would be the best way to read a button. Well, it is not, because of something called debounce. So what exactly is debounce? Okay, so debounce is this phenomenon that happens when the button contacts don't touch the button contacts don't come into contact perfectly, and this results in sort of a really random or like messed up waveform. So let's just see what this looks like. I don't think I can. I will try to do it on the scope, but I'll just draw out what actually happens. So assuming that we have a simple pull-up button, sorry, pull-down button. So this is pull-down, this is the pin, and of course we have the button over here connected to 5 volts. Okay, so let's say we press the button, so this should go to 5 volts. So instead of seeing this, which is say if the button is pressed at T, we expect this to just go up to 5 volts and just stay there, right? This is what we expect. But what happens is, instead of this, it will actually go up. Maybe it would go up at first, and then it would just suddenly bounce down, bounce up, bounce down, bounce down, and then finally just stabilize, because what's happening is that the internal button contacts they're not perfectly smooth. They are like have physical imperfections. So the first point might come in contact with another point, and then maybe it might, for some reason, lose contact, and then another point might come in contact and then lose contact. So you have this bouncing up and down, and this bouncing can be so bad that it can even go back to 0. So what happens if you want to measure a very short button press? You just want to press it once, and you want it to detect the button press. Well, what's going to happen is the button is not going to react in the way that you think it would, because this bounce might trick the microcontroller into thinking that the button actually was released, but in reality that's just because the contacts are not not perfect, and this bounce is just a natural process that happens when you have an imperfect physical button. Okay, so over here I've wired up my DSO to the button. So the positive connection goes to basically goes to the point where the button is connected after the resistor. So it's resistor from it's from 5 volts through the button, and then the point where the pin is connected to, that's where the probe is connected, positive end of the probe. The negative end of the probe is connected to ground. And so when I press the button, we see that this thing jumps. So I'm not that interested in the overall result, because I know it's going to jump. I'm interested in the exact waveform of when the button actually is pressed. So I'm going to go and edit the settings of the DSO. So zoom in for a bit. I'm going to change this to rising edge, because I'm expecting the thing to go up. So change it to detect on rising edge. I'm going to change the time to even, wrong direction, to really short, because I'm going to want to catch this bounce, and I'm going to set this to single, and I'm going to change the I'm going to move this a bit higher so that it will detect when the bounce happens, which I believe should be pretty large, at least not so close to the current axis position of this thing. So okay, so when I press the button, it stops, but I don't see anything. Okay, maybe it's even faster. So we're gonna resume it. Okay, I suspect that maybe this has to go up as well. No, this is the baseline. Okay, that's strange. So maybe I need to decrease this to capture more. So increase this to capture more, maybe 0.1 milliseconds. There we go. Okay, so we see this waveform of it going up. Maybe I can drop this down back to 50 microseconds and run this again. Excuse me, what? Okay, it captured slightly more detail. Try again. Okay, Now let's drop it back down to 20. Oops. Okay, that 20 is too little. It's not capturing anything at 20. At 50, it's capturing this. So you can see that it's already quite clean. We don't have crazy bounce that we've seen, where we don't see this thing drop all the way back down to 0. It actually just bounces a bit at the top over here and then smooths out really quickly. So this button is pretty good. It doesn't have a very bad bounce profile, but some buttons might not be so good. They might actually drop all the way back down to 0, which would be a false trigger. So that's why we must take action to not be tricked into changing the state of the button press when we see this 0, because we might still be in the phase where the button is still bouncing. Okay, so how do we deal with this problem? So let's revisit the problem again. The problem is that when we press the button at, let's say, t equals 0, there's going to not be a smooth increase and then stagnation, but instead it's actually going to go up and then go bounce, 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 bounce. And we don't actually know how bad the bounce is, but let's just assume the worst case scenario. But after some time, let's just say, let's call this t, debounce or something like that, and it's going to smooth out. So we know that eventually it's going to smooth out, and we know that when it smooths out, it would definitely be at 5 volts, because heck, if it doesn't, then that button is defective. So we know that it's going to smooth out at 5 volts, but we don't know when, and we cannot possibly take our reading here, because when we take our reading here, are we just going to think that this is low, or because it's below the halfway mark or something, and it's not going to be, it's going to be tricked into thinking that the voltage is is a low voltage, because the Arduino the Uno has a cutoff. I'm not sure what it is, but let's just say that this dips below that cutoff and it thinks that it's low, but actually it's just bouncing. So there are a bunch of methods to solve this problem. So I'm just going to introduce the software methods in this video, because this video is a beginner's tutorial where software methods are most suitable. So the idea is that we check when the button was pressed. So we look at when this thing goes up, because we know that it has to go up eventually, right? When you press the button, it goes up, it just comes down and does this nonsense, but we know that it goes up. So this is the point where button is pressed. And when the button is pressed, we are actually going to do something of a wait. So we're going to wait for some period of time, and then after that wait, we're going to then read the button again. So we're going to read it, and this is going to be our final value. So we know that this bounce is going to take some time, and we're going to let the bounce do its thing. But once that time has elapsed, we are going to take the value, and this is going to be final. So the idea is we want to get this value, and we know that it's going to be correct because the bounce has already been finished. So let's go back to the IDE and implement it in some code. Alright, so we're in the Arduino IDE, and let's get to work. So we're going to create 2 global variables. So global variables are declared outside of these functions, because when you declare a variable in a function, it's only available to in the function itself. So I'm going to declare a variable called unsignLong, call it debounce timer, and I'm going to set it to 0. So this is available anywhere in the sketch, not just in the setup or loop function. Next, I'm going to declare 3 Boolean variables. So Boolean, let's call the first one current button state, and let's call the second one, okay, let's set that as false. Let's call the second one last button state. Let's set that as false, and let's call the final one current reading, and let's set that at false. So we have created 3 Boolean variables. These will store various things. We will discuss what these store later on. So in void setup, we can leave everything as it is, and let's go straight to void loop. So the first thing we need to do is we need to check if, okay, before that, let's actually write what we want to do. So okay, we're going to use a multi-line comment. So the goals of this code is to, number 1, we need to detect when the button was pressed. Okay, so we need to detect when the button was pressed. Number 2, we need to wait for a period of time to pass. and then we need to record. We need to read and record the value of the button after set time has elapsed. And of course, number 4, we need to print out this value to the serial monitor. So this is kind of optional because this is ours for a specific case. Perhaps for your actual code, you might want to write the value to LED and whatnot, but in this case, let's just print out the value to the serial monitor. So the first thing we need to do is, let's do 1 first. So objective 1, we need to detect when the button was pressed. So we need to basically take a reading and then detect when it was pressed. So let's say reading, let's assign the current value of the button. So digital read button, which is 10. Let's assign the current state of the button to this reading variable. Okay, and then that doesn't complete number 1 yet. Then we're going to say if. So an if, this is an if condition, means if this condition in the brackets is true, then we run whatever is in the code. So if this reading is not equal, so if it's different from the current button state, so this is current button state, if this is different, then we need to do stuff. So we have detected that the reading is different. So we've detected that the reading is different from the current button state. So we need to begin the second part, which is to wait for the period of time to pass. So we do that by setting debounce timer equals to millis, because this resets the debounce timer. So what does that mean? Well, we'll see it soon enough. So we set debounce timer to millis. This means that, okay, so millis is this sort of function in Arduino the IDE that basically just is the value of the amount of milliseconds that has passed since the code has started. So it's the time since boot. It is dynamic, it's always changing because the time is always going forward. So we set debounce timer to this value. So this means that we update debounce timer with this snapshot of the time where this happened. Okay, so now that happens, we're going to do part 2, which is to wait for a period of time to pass. So we say if millis minus debounce timer is larger than some value, say 100. So what this does is, let me put this in brackets for greater clarity. What this does is that if the current timestamp minus this snapshot time is greater than 100, so this means that millis is going to be increasing constantly. Debounce timer is going to be stagnated at this timestamp. So if millis is 100 milliseconds greater than debounce timer, which means that if 100 milliseconds has passed since this snapshot was taken, so essentially we wait 100 milliseconds. Okay, if that's the case, then we need to check if we need to basically do stuff, right? We need to see if we need to therefore do part 3, which is to record the value of the button after the set time has elapsed. But we need to check one more thing. Well, why do we need to check one more thing? This is because millis minus debounce timer can be greater than 100 in many cases. Well, the most obvious case, actually, in fact, it can be greater than 100 in almost all cases, because if the button is not pressed for some time, millis is going to increase to a very big number. Debounce timer is not going to be called because the reading is not going to change from the current button state. So therefore, this is going to get very, very large. This is not going to change. So this can easily be greater than 100 in many cases. It can be greater than 100, in fact, most of the time. So this alone is not a good indication that the time has elapsed, because, well, if we don't check that the button state has changed, then even if the button state hasn't changed, then this will still return true. So yeah, I'll explain it more as we move along. I'll come back to this later. So, well, we're going to check that our reading is indeed still different from the current button state. So it's the same check as this here. Well, what we're saying is that if some time has elapsed since this was last called, we're going to check that, well, this condition where this was called is still true, because this was only called because this was true. So well, if the time has passed and this becomes greater than, well, this minus this greater than 100, this means that some 100 milliseconds has passed. We're going to check that this condition is still true, because that would mean that this was called, this was indeed called 100 milliseconds before. If this is not true, then this was not called 100 milliseconds before, because this would have called this if this was true, or perhaps if this statement was true. Therefore, it means that this is just the millis growing bigger and the bounce timer not moving, so it's just going to happen, because as the code runs and nothing changes, this is naturally going to become true in many cases. So this checks that this was indeed called beforehand. So this is going to prevent us from, you know, accidentally doing stuff when we aren't actually, the button actually isn't pressed. So if the reading is different from the current button state, then, well, we know that this has been called, so the button state has changed, and we are going to actually take the final value. So we're going to set our current button state to our we're going to take well, let's see here. So we can actually take the digital read, or we can actually take reading. So how does this make any sense, right? Because the idea is that in the time within 100 milliseconds, this code would have executed many times. So this might not have been true, but this doesn't mean that this doesn't happen, because even if this doesn't occur, even if this entire code block doesn't execute, this code block still executes, which means that reading is constantly being updated with the most up-to-date value of the digital pin. So this can actually just be set to reading, or if you fancy, you can set it at digital write, or digital read 10, but this is an additional operation. This has already been done before. You don't need to take the reading twice in a short period of time, because, well, that's just a waste of resources, so we can just do this. Okay, so we're going to set the current button state to be reading, and this means that we are going to essentially update this current button state with our reading. So therefore, this is no longer going to be true, because this is a direct contradiction to this. If the button state is equal to the reading, it cannot be different from the reading. And so when the code comes around, this is not going to execute anymore, which is fine, because, well, the button state has been finalized. We are setting the button state to its final value. We don't want anymore. We don't need to wait anymore, because we've already done 1, 2, 3. We're just going to move on. So at this point, well, we need to update the millis, because, well, that's just because we have used the millis and we are done with it. We can update it, although it's not going to do much, because millis minus debounce timer is going to increase way beyond 100 anyways, even if we update it, because if the button is not pressed for a period of time, this is just going to increase, this is not going to increase, this is just going to be true for many cases. But nonetheless, we will still update the timer for, I don't even know, I think it's just for habit, out of habit. And of course, we also need to update the button state. So if the current button state is equal to reading, okay, no, we don't do that. We need to okay, we just leave, because we are done. We have set the current button state. We know the current button state has been set. We are going to leave. So we're going to get out of here. So let's get out of this if loop, sorry, if condition. So this 3 has been done over here. So current button state is reading, that sets the current button state, and we're going to print out this value. So when we print out this value, well, that's quite simple actually. That's why we created this last button state variable. We're actually going to compare the current button state with the last button state. So if it's equal, not the same, this means that the button state has changed, and we're going to do 4. So this is where 4 comes in. We print out stuff. So I'm going to print out the button state, current button state, and then we're going to update the button state. So we're going to update the button state. I'm just going to copy this because I'm lazy. I'm going to update the button state. So the last button state is going to be equal to the current button state, because we have already done what we need to do. If let's say we wanted to use the button state to do stuff, we would do it here. So if let's say I want to turn on LED, etc. We would do it here, and then we would set the last button state, the current button state to update the last button state. So the reason why we do this is because we want the last button state to be a reflection of the current button state, because in the future when the current button state does change due to this, we don't want to be stuck on the last button state. We want it to, the previous last button state, we want it to update to the button state that was in the past, which is the current button state. So essentially the current button state becomes the last button state. So I hope that kind of sinks in, you know. In any ways, I don't like this method of debounce. We will see a more intuitive method later on, but that's just how this debounce works. So while that's done, then alright, I think that settles it. Let's do some checks. Let's check that we did not make any syntax error, and let's proceed to upload this code into the board and see how it performs. Hopefully we didn't make any like logical semantic errors, and we should see it work. Okay, turns out that I forgot the naming of my stuff. This is actually reading, not current reading, so let's just change that.
A few moments later.
Okay, so I realized I made a pretty big mistake, is that this should not be current button state, this should be last button state, and this last button state is not being used in the correct way. So last button state is literally the last reading that was taken. So the last reading updates itself. So if last button, so basically if once this whole loop has completed, then the last button state is going to be, sorry, this is wrong. This should be current button state, and this is going to be last button state. So when this whole thing is gone, when this whole loop is finished, then we literally update last button state as the reading, and we do that because we want to make sure that this only happens once. So once this happens, the bounce timer sets millis, then this is true because this is the exact same thing. So if this happens, and this sets the last button state to the reading. So this can no longer be true, because if last button state is equal to reading, then reading cannot be different from last button state. So this basically prevents this from happening again, which prevents the case of this never becoming true, because if this were to if reading were to constantly be not equal to last button state, then this debounce timer would constantly be reset to be the millis, and this would never become true, because imagine every loop we come around, last button state is not equal to reading because we did not update last button state after the loop before the loop had ended. Well, this would then mean that debounce timer is updated to be millis and minus debounce timer would not be greater than 100, and therefore the reading, this whole chunk won't even happen. So this is why we need to set, basically last button state is not the final, okay, I'm just going to write this down, is not the final, the previous final button state, but rather the last, it should just be called last reading. I think that is a better way of doing this. Well, I was reading the official debounce example, and I was confused by the naming, so when I did this sketch I thought that it was the previous final button state, but it's rather the last reading that was taken, and it's just used as a way to prevent this from occurring every time. So this only occurs once, this is set, this does not occur until the reading changes. So the reading changes how? Well, the digital read changes. So it means that if the button state does change, this thing can basically happen once and then happen no more until the reading changes again. So that's exactly what it does. Okay, so now that we remove that, we need to reinsert our serial print. So if the button state is equals to, well, this, okay, so let's see where to put this. So, well, what happens here is that the current, but if the reading is different from the current button state, well, this updates. So this also happens only once, because this basically prevents this from happening over again. So we can safely put our serial prints here. So button state is, this will only happen once, and then we say serial.println, and we do the exact same thing, just that we put it into this condition instead. So this can be reading, and then this should work, hopefully. So let's test it out. Okay, so we are back at the Arduino board with our serial monitor open, and let's see what happens when we press the button. So button state is 1, button state is 0, button state is 1, button state is 0. So this debounce code works finally, and that's how it does. So we literally waited for the debounce to finish, and then we took a reading. So that's what this code does. But the key assumption here is that we know how long the debounce will take, and we can provide a value that is going to be greater than that debounce reading. So in this case, we chose the arbitrary value of 100 milliseconds. But what if we don't know what the value is? How do we ensure that the debounce how do we ensure that the code only takes the reading after debounce has finished? So this second example will use that technique instead. Okay, so for our second technique, we are going to craft the same scenario when at time t, the thing goes, the button is pressed, and so it bounces up, then it does this weird bounce stuff, and then it finally settles on a high voltage. So this is where the debounce is finished. We want to be able to tell when this debounce is finished, and then we are going to take the reading here. So take reading here, and we know that this is going to settle. So how are we going to do that? Well, we can sort of use a bit of the properties of this bounce, which is that if the bounce is severe enough, we will literally see, the Arduino Uno would actually read 0 here, so it actually would think that the value went from high to low, and then maybe if this was bad enough, it would also think that it went up back to high, and then it went back to low, and so it would actually see a bunch of oscillations between high and low, and then finally, of course, back to high. So we can actually use these to help us deduce when the bouncing has stopped. So let's head back to the Arduino IDE and code it. Okay, so I'm back at the Arduino IDE, and I've opened a new sketch. So because I feel it's easier and it preserves my work. So I'm gonna just copy over the stuff that we've done. So the bounce time equals 0, and I'm going to of course set up our various stuff. So series of begin 15200, and then we're gonna set up our pin mode 10 and input. So that's gonna be that. Okay, so now the magic comes in the loop. So let me just take our goals and put them over here so we know what we need to do. So the first thing we need to do is, okay, we need to edit the goals first. So we don't wait a period of time to pass, we wait for the debounce to finish. So that's what we need to do after debounce has finished. So we need to wait for debounce to finish. How do we do that? Well, let's find out, and we need to record the value of button after debounce has finished. Okay, so the first thing we need to do is, well, let's create some variables to store our data. So we call this the reading. Let's say it's false. And we have our last reading, which is also going to be false, and our last button state, which is also going to be false. So, well, reading is equal to digital read 10. So that happens all the time. So we need to detect when the button was pressed, right? So, well, we're going to do that now. So if reading is different from the last reading, well, that detects when the button was pressed. So this is 1. Okay, so when reading is different from last reading, what we're going to do is we're going to actually update the timer. So that's something that we're going to do. A bit different from the previous one. So we're going to say the bounce timer is equals to millis. So what is this going to do? Well, every time the every time the reading is different from last reading, we're going to update the millis, and we're going to set last reading is equals to reading. So what this does is that if, say, the reading changes, well, we're going to reset the debounce timer. So we're going to take a snapshot of the time that it occurred, and then we're going to also set the last reading to reading, which is essentially just reset the last reading flag. So this resets the flag, which means that if the change happens again, it will be able to update the millis, update the debounce timer again. So that's what it does. It basically allows this debounce timer to be reset every single time reading changes, because the last reading is updated. So it will trigger every time the reading changes from true to false, and then false to true. It will every single time trigger this debounce timer to be reset. So that's what we do. So this is detect when button is pressed. Now let's do 2, which is if millis minus debounce timer is greater than some value, so that's 100. Let's say 600. Now this is 2. So how does that work? So basically, the idea is that if the reading keeps bouncing around, then that means that, well, this is going to be constantly reset. So debounce timer will be constantly set to millis. Well, so this is going to be equal to 0. The moment debounce timer is set to millis, well, millis minus millis is 0. So this is going to be definitely larger than 100. Sorry, smaller than 100. So this is not going to be true. And as long as this thing bounces, well, this is going to be constantly updated to millis. This is going to be constantly set to 0. This is never going to be true. So this is a way of waiting for the voltage to settle down, because as long as it bounces, this is never going to be true and this code will not run. So whatever code runs, this means that, okay, the bouncing has stopped for 100 seconds, because the moment, sorry, 100 milliseconds, because the moment anything within 100 milliseconds, the moment if there's a bounce where the reading changes, well, this thing just gets set to millis and the whole process has to be reset. So this basically checks that reading has not bounced for at least 100 milliseconds. So that's what it does. It checks that the reading has not bounced for 100 milliseconds. Okay, so now that we know that the reading has not bounced 100 milliseconds, we can proceed to print the value, because we know that the reading is going to be, or perhaps let's say current button state is going to be equals to the reading. So there we go. So we're going to print the reading. Okay, so we can upload this code now, and there's actually a small problem which I will address, but let's just upload this first and see what happens. Okay, so the small problem that we have is that when we open the serial monitor, we are spammed with this serial prints. But when we press the button, we see that this thing does work as expected. So, well, we know that it works, but we are being spammed with print. So let's see why this happens. Okay, so the reason why this happens is because when we go over to our code, we see that millis minus debounce timer is larger than 100. Well, if after the debounce timer has not been, basically after the reading has settled down and this has not been triggered for some time, this is going to be increased. This is going to be greater than 100 because millis is going to constantly increase. The debounce timer is going to be stay the same, and so this is going to be true for basically forever until the button is pressed. And this means that this is going to be spammed out, because every time this is true, this gets printed. So if this is true for every single cycle of the loop after 100 milliseconds after this has settled down, well, this is just going to be printed out forever. So to prevent this from happening, we're going to use the final Boolean variable we've created, which is the last button state. So if the reading is different from the last button state, well, then we print, because that means that the reading has changed. Sorry, last button state. It means that the button state has changed, and we're going to print it out. Okay, so we're going to print it out, and the important thing is that we're going to set the last button state to the reading, so that this is not going to be true the next time the cycle runs. Because, for instance, if this cycle runs, reading is not equal to the last button state. Okay, we print this out. We set the last button state to reading, and from now on, the last button state is going to be the same as the reading, so it cannot be different from the reading, and therefore this is going to not be true and this will not print. So if we upload the code, we should see that this actually dramatically decreases the number of times the serial print is spammed. In fact, this will just mean that the serial print only prints when the button state changes. So let's upload the code and see what that does. Okay, so I've uploaded the code and let's test it out. So there we go. When I press the button, it goes to 1. When I release the button, it goes to 0. Perfect. So we have ourselves a working debounce code. The final code I'm going to present is going to use a different idea. It's not actually going to wait for the debounce to settle. It's actually going to integrate the various readings over time. So what the idea is okay, let's copy over the same template for our goals. Is we are not going to attempt to wait out the debounce. We're actually going to just take readings at intervals, and we're going to add these readings to some counter, and then we're going to change the output or set or print out the value of the print out high when the counter reaches some cutoff, and vice versa for low. So how this is going to work is quite simple. We create a counter, we initialize at 0, and we simply, okay, I'm going to put in the standard stuff. Okay, and I'm going to basically take a reading from the we're going to take a reading from the pin. So if digital read 10 is true, basically if I don't put equals true, this just means that if it's true, then if this is true, then this becomes if true, which is of course going to execute the stuff in the code in the curly braces. So if digital read is 10 is true, then we're going to increment the counter if the counter is smaller than equal, say, let's say the cutoff is 10. So if the counter is smaller than 10, we're going to increment the counter, else we're just going to not do anything, because if the counter is already at 10, we're just going to leave it. Okay, and if it's not true, if digital read is false, then we're going to decrement the counter if it's larger than 0. Okay, if it's smaller than, if it's equal to 0, then we are not going to do anything because we cannot decrease it further than 0 since it's an unsigned integer, so we need to just leave it be. Okay, so if the button reads a high, then we're going to increment the counter. If the button reads a low, we're going to decrement the counter, and eventually let's just say if that we want to do this at a particular time interval. We're not going to do this instantaneously because we don't want to take readings all in one shot, because if we just run the code as it is, this is going to take the readings almost instantaneously. So digital read is just gonna read at like a ridiculously high rate, at a ridiculously high frequency, and this is gonna reach 10 very quickly. So one thing we could do is we could increase it to 100 so that, sorry, what am I doing? We could increase this to 100 so that it would require a lot of increments to get there. So that's one method. Or I'm going to actually just let it read at a particular interval. So I'm going to go up here and create a timer. So I'm not going to call it the let's just call it integrator. I can't even spell now. Integrate, I don't think there's an R. Timer equals to 0, and I'm going to say if this timer is going to be, okay, if millis minus this timer is going to be greater than some interval, so that interval, let's just set it at 10 milliseconds, I think that's suitable. Well, then we're going to do all this stuff that we've defined here. So if this timer is great, if this timer becomes, okay, wait, I need to move this. Okay, this goes in. If this timer becomes greater than, if millis minus this timer is greater than 10, which means every 10 seconds we're going to do whatever is here, and then of course we have to update this. If not, this will constantly be called, which is not what we want. We want this to update. Okay, so this is one way of doing it. Another way of doing it could be, I'm going to just copy this over. We could actually just use the modulo function. So what is a modulo function? It finds the remainder. So basically, millis modulo 10 means find the remainder when millis is divided by 10. So how does this work? Basically, if millis is a multiple of 10, the remainder becomes 0. So every 10 seconds, because when millis is divisible by 10, it means that it's a multiple of 10. So it will only return 0 when millis is every interval of 10. So that's another way of doing it. Then you wouldn't need to create this random variable over here. You would just use this. We won't need to create a variable, but okay, I would just use this for now because I think that's it's a bit cleaner. I don't know. We don't have to use this modulo function. Okay, sure, so we use that. Okay, so if it's true, then we count up to 10. Once we reach 10, well, if we reach 10, then the moment this is equal to 10, then we need to do stuff. So, well, let's create yet another variable. Let's create the final button state. So this is not new to you. In the previous example, we used that to prevent spamming of the serial monitor. So else if the button state is false, then we will print out stuff. So if it's false, so we will print button state, and then we would say, okay, we can just print directly here, because if it's more than 10, okay, if it's 10 or greater, which actually it can only be a 10 because it cannot increment above 10. So as long the moment it is equal to 10, we're going to say the button state is true because we have reached the high cutoff. So 10 is the high cutoff or high threshold. And conversely, if it reaches 0, then we are going to print the button state to be false, and of course we need to update the button state, because if not, then we're going to get spammed. Our serial monitor is going to get spammed. That's not what we want. We just want it to happen once. So we use this flag to basically invalidate itself the moment it is validated. So when this is false, then we need to immediately set this to true. So when do we set this? So when the question is, when do we reset this to false? Well, that, hold up, wait a minute, button state, okay, this technically should be reversed because the button state is true, then this becomes false. Well, I don't think that affects anything, but let's just do it for fun. Okay, so when do we reset this? So, well, if the counter is incrementing, which means that we are moving away from the, okay, wait a minute, I think this is not a good way to do it. Let's use a different way. So, okay, so let's just say if counter reaches 10, okay, let's just not care about this thing for now. Let's just say if the counter reaches 10, then we will set button state to be true, okay? And if counter reaches 0, then we set button state to be false. So what this means is that we're just going to set the button state for now, and then we deal with the button state later on. So, okay, so the button state reaches, okay, so let's just create another one, which is, whoopsie daisy, button last state. So that's false as well. So if the button last state is not equal to the button state, then we will do stuff. So serial.print button state, and then we will print out the button state. And of course, we have to update the button state, button last state with the button state. So that will prevent it from being spammed, because the moment this happens, the only way that this can become true again, or button state be different from button last state, is if the button state literally changes. So it means that we must have the counter reach 10 or the counter reach 0, which will only happen if enough increments happen. So I think this should work. Let me just upload this and let's see how it fares. Okay, so we are back at the board and let's test it out. So 1 0 1 0. Okay, so it seems that this method works and we have gotten ourselves yet another successful debounce function. With that, we've come to the end of the video, but before that, I would like to make a few comparisons between the various debounce methods that we have seen. So let's start with the first one. This is the standard debounce method, or the one that you actually can find under the examples. If you look under digital, you will see this debounce, and this is pretty much the same idea. I actually drew a lot of reference from this idea, from this sketch, and this is the first implementation that we have. The second implementation was the one where we wait for the debounce to finish, and the last implementation was the one where we used a counter and we counted up when the button was pressed and counted down when the button was not pressed. and then we would set the button state when the counter reached high cutoff or low cutoff. So that's the ideas. I feel that the first method is basically the second method, but I feel the second method is a bit better because it waits for the debounce to stop. This is better because we don't have to make an estimate for when the debounce will be over. We can simply just let the debounce itself dictate when we are going to take the reading. So I feel that this is better. In terms of the memory and the number of variables used, I think they are both quite similar in terms of the total number of variables being declared. But I feel that this code is slightly simpler to implement because it's the logic is a bit clearer, and the code also is by design slightly shorter. I think it also boils down to your familiarity with both of these algorithms or both of these methods. The third method is a bit of a wild card. I've actually didn't realize it, I didn't really think of it until I read an article by the I will link the article in the description below. I can't remember who exactly wrote it, but I remember that I saw this and I was thinking, okay, this is kind of interesting as well, so I decided to implement it in this video as well. So ultimately, the decision to use a debounce algorithm is pretty subjective. It depends on your personal taste, but eventually I hope that we can all walk away with the understanding that buttons are physical, they are imperfect devices. They will exhibit certain imperfections and noise and bounce, and we need to take steps to deal with it. So software debouncing, these are the three main methods. There are actually a lot more, as you can see in the link that I will link in the description below, but these are the three methods which I find are the most accessible and the easiest, perhaps the first examples that come to mind. So in the future, we may be looking at hardware debouncing, which is using hardware to reduce the noise and also to perform the same debounce, the same ideas of debounce, which is to only return the final state when the voltage crosses a certain threshold. That is will be with the use of Schmidt triggers and other interesting stuff, but that's not going to be in the scope of this series. So okay, till then, take care and I'll see you next time.